Okay, we're going to continue on with limits and then introduce continuity, which involves limits. And so let's look at a theorem here. And here's the hypothesis of the theorem. If the limit as x approaches c of f of x equals L, and the limit as x approaches c of some other function g of x equals m, then we have a whole bunch of limit laws. And so one, the limit as x approaches c of f of x plus or minus g of x equals L plus or minus m. So the limit distributes over a sum and difference. Okay. And on 2, if you look at the limit as x approaches c of, if you take one of the functions and multiply it by a constant, and so here k is just some real number, then the constant comes out front, and then you can compute the limit. Oops. And this is k times m. So you can get that pesky constant out of the way. Okay, 3. If you look at the limit of the product of the two functions, so f of x times g of x, well, this is just equal to the product of the limits. So that's nice. 4, the quotient rule. If you take the limit as x approaches c of f of x over g of x, this is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x, and this is just L over m. Okay, and then we have a power rule. So if you take the limit as x approaches c of the function f of x raised to some power, what happens is, because the power function is continuous, you can slide the limit inside. So this becomes the limit as x approaches c of f of x, all raised to the n, which is L to the n. And this is true if n is any real number. So n could be a fraction, right? Or a positive number. And then that falls into this idea of the root. If you take the limit as x approaches c of the nth root, which is just 1 over n of f of x, this is the nth root of the limit as x approaches c of f of x, which is the nth root of L, which is L to the 1 over n. So all these rules apply, and they're very, very straightforward. And let's use them to compute some random, this is just algebra here, random limits, right? So example 1. Let's compute the limit as x approaches c of 3x cubed minus 2x squared plus 7. And because the limit distributes over sums, this is a lot of writing, but here we go. The limit as x approaches c of 3x cubed minus the limit as x approaches c of 2x squared plus the limit as x approaches c of 7. So we've used property 1, right? And for each of these limits, there's a constant. So we'll take this constant here and get some color going, right? This is the k from above, so that's going to come out front here. And similarly, that guy's going to come out front here. So we have 3, I'll do this, 3 times the limit as x approaches c of x cubed minus 2 times the limit as x approaches c of x squared plus the limit as x approaches c of 7. Okay, so this is 3 times c cubed. So now you just plug it in. Minus 2 times c squared plus 7. And there it is. Here's example 2. Let's compute the limit as x approaches c of x cubed plus x plus 1 over x minus 5. Well, this is rational, so it's this one here. It's a quotient. So this becomes the limit as x approaches c of x cubed plus x plus 1 over the limit as x approaches c of x minus 5. And then we use the sum. So now we have the limit as x approaches c of x cubed plus the limit as x approaches c of x plus the limit as x approaches c of 1 all over the limit as x approaches c of x minus the limit as x approaches c of 5. And this is c cubed plus c plus 1 over c minus 5. And then one more. Let's compute the limit as x approaches 3 of the square root of 4x squared plus 7. And we can slide the limit inside here. And then, separate it out. Oops. And then taking all the grubby steps here. 4 times the limit as x approaches, this is supposed to be a 3, not a c, of x squared plus limit as x approaches 3 of 7. And this becomes 4 times 3 squared plus 7, which is what, 36 plus 7. And that's the square root of 43. So that's the limit. Okay, here's the next theorem. We'll call this theorem 2. If p of x is a polynomial, then the limit as x approaches c of p of x is just p of c. Just evaluate. Okay. So now we're going to talk about continuity of functions. Now first what we do is we define continuity at a point, and then we define continuity over an interval. And that interval might be all real numbers, or it might be some subset. Okay? And so one of the reasons I like this book, and I've been working with it for so long, is because it has these boxes that show up in every section. And the box kind of highlights the main points or the main technique. And so, so continuity of a function basically means as the function is going through its game, its life, your pencil never leaves the board, right? So if you went like that and then picked up, you can't see I'm picking my pencil up, but then it restarted down here and like that, you'd see that there's a big discontinuity here, right? Or even if you have just a hole, right? So at this point, whatever it is, the function is discontinuous, and here it's got a jump discon. So as long as your pencil stays on the paper, the function is continuous. And that's the sort of layman term way of speaking of continuity. But we have to be rigorous in mathematics, so let's make this a rigorous definition. And this is synthesized in the box on page 94 in your book. I think they call it the continuity test, but it's really the definition of continuity at a point. So here we go. Definition. A function f of x is continuous at a point x equals c if the following three conditions hold. Number one, f of c must exist. Can't have a hole there. Okay. 2, the limit as x approaches c of f of x must exist. And 3, number 1 has to equal number 2. In other words, the limit must equal the function value. So let's look at some non-examples first to show how this definition works. What's a function I can use here? Is the function f of x equal x squared minus 1 over x minus 1 continuous at x equals 1? Well, we showed before in the last video, we showed that the limit as x approaches 1 of f of x is 2. We already did that. So this piece is right? The limit exists. It's a two-sided limit. It exists and it's equal to 2. Okay? So we showed part 2 is true. But what's part 1? Part 1 says f of 1 here does not exist. It's undefined. So part 1 is broken. Therefore, it's discontinuous at x equal 1. Okay. Okay, how about this? So here's another, can I do a non-example? I can. Let me think here. Let me think really hard. Let f of x be the absolute value of x over x. And we're going to look at the limit. Sorry, we're going to look at, first of all, what's f of 0? It's 0 over 0 and it does not exist. So the function is discontinuous. So you don't even have to check for the limit, because even if the limit does exist, which it doesn't, then it's discontinuous there. And if you graph this, it's 1 up there and minus 1 down there. So the right hand limit's 1, the left hand limit's negative 1, and they're not equal either. So there's no two-sided limit, and f of 1 is undefined. Sorry, f of 0 is undefined. Let's do one more here. How about an actual example? Is f of x equal x squared minus 1 over x minus 1 continuous at x equal 2? So 1, f of 2 is 2 squared minus 1 over 2 minus 1, and that's 3. 2. The limit as x approaches 2 of x squared minus 1 over x minus 1 is the limit as x approaches 2 of x plus 1, which is equal to 3. So in this definition, part 1 is correct, and part 2 is correct, and what we want is 1 to equal 2, and 3 equals 3, so 3 equals 3, hence f is continuous at x equals 2. Okay. So next definition. A function is continuous on an interval if it's continuous at each point on that interval. And that interval can be all real numbers. So this is the definition of continuity on an interval. And it's possible that the interval is minus infinity to infinity, right? So like the line f of x equals 8x is continuous on all real numbers. Okay. There is a minor thing to contend with here, and that's what happens at endpoints, because this limit in the definition here has to be a two-sided limit. So here's a good example. Let's discuss the continuity of the function f of x equals 4 minus x squared, square rooted, at x equals plus or minus 2. And these are the endpoints because the domain is minus 2 to 2. Right, so if you graph this, it's the upper half of a circle of radius 2. Okay. And the question is, at the point 2, 0 and minus 2, 0, is f continuous? Well, if you just apply the definition straight away, f of 2 equals f of minus 2 equals 0. So the functions exist there. But if you take the limit as x approaches 2 of f of x, what does it equal? Well, you don't have a two-sided limit because to the right of 2, the function doesn't even exist. So we make a special exception for endpoints. So at 2, you really want to look at you have to look at the picture of the function, and if the left-hand limit, so as I come along here, if this thing exists, which it does, it equals 0, then it's okay, and we say the function is continuous at x equals 2. Similarly for x equals minus 2. And so, yeah, we make an exception at endpoints. You look at the one-sided limit that's appropriate for the point. Okay. And this leads to a very famous theorem called the, any famous theorems get bold lettering. The IVT. Intermediate value theorem. So if f is continuous on the closed interval AB, and y naught is any point in the y interval, so this is going to be f of a to f of b. So if f is continuous on AB and y naught is any point in this y interval, then y naught equals f of c for some c in the x interval AB. And that's a really hard theorem to take in. The picture that goes with it is much more intuitive, and it's the way I remember it. In fact, I normally would draw the picture first just so I could make the theorem from it. So, all right, so unraveling this thing, we have an interval a to b on the x-axis. And then up here, I'm just going to put some point f of a. And then up here somewhere, I'm going to put some point f of b. And since f is continuous, we know that this doesn't leave the paper, right? There's no holes, no breaks, nothing. And what the theorem says is, if you give me any y naught in this interval here, any one of them, just put some random y naught here, then it's going to come over here, and there's going to be some c down here such that f of c equals y naught. And we can use this for a lot of cool stuff, mostly to define the mean value theorem, which I spoke about earlier. Okay, so let me go in here. I didn't write down the guided practice, but I picked it. So here we go. GP. Where are you? GP. Okay. At what points, I should say, this is how the book writes it, but I should say, what are the intervals of continuity? So, but it says at what points is the function at what point or points is the function f of x equals one over x plus 2 squared plus 4 continuous. And like a lot of things in mathematics, what you really want to do is look at this backwards and ask yourself, where is it discontinuous? And prove that. Right? So that's the better way to think. Like, what are the discontinuities, if any, of this function, and why is it discontinuous at that point or those points? Okay, I'll see you in a minute.